Welcome to this video in which we will solve for the tensions in each of the members of this truss by using the method of joints. This truss has 7 members and 5 joints. Each member is 1 meter long, so the truss is made out of equilateral triangles. So every angle in every triangle is 60 degrees. The truss has a load of 1 kilonewton at the center. With these dimensions and load, this truss might represent a small footbridge with a fairly chubby person standing in the middle of the bridge. We begin by drawing a free body diagram of the whole truss to find the reaction forces. We will then go joint by joint through the truss to find the tension in each of the members. Here is the free body diagram of the whole truss. We have joints everywhere the members meet. And then we have the following reaction forces. On the left we have a pin joint, so basically our entire truss is free to rotate. This will give us an FAX. Whoops, this will give us an FAY. Don't know what happened there. FAX. And then here we have an FEY. And at the center of the truss we have a 1 kilonewton load. Each of the members of the truss is 1 meter long. Again, let's look at the entire truss first to find these reaction forces. If we look in the x direction, the only force in the x direction is FAX, and that's equal to 0. So there's basically nothing pushing the truss either to the right or the left. Next, let's look at the moment about A. Summation of the moments about A is equal to 0. Okay, we'll choose A because we have 2 forces going through A, and so if we choose A about which to compute the moment, then it makes life a little easier. We have only 2 forces we need to look at. So we have 1 kilonewton going downwards with a moment arm of 1 meter. This is going clockwise, so we'll have minus 1 kilonewton times 1 meter plus FEY times 2 meters. Okay, this force here acts through a moment arm of length 2 meters. And this is equal to 0. And once we solve this for FEY, we get that FEY is equal to 500 newtons. Okay, so the summation of forces in the y direction is equal to 0. And we have FAY minus 1 kilonewton plus FEY is equal to 0. We know that FEY, this guy is minus 500 newtons. No, that should be 500 newtons. This is an arrow, not a negative sign. Okay, something was going to be terribly wrong there. We can solve this then for FAY to get FAY is equal to 500 newtons. Okay, so what this tells us is there is no horizontal force, and the load of the bridge of 1 kilonewton is equally distributed between the left and the right support. So now we can go through the truss joint by joint to calculate the tension in each of the members. We assume that joints are held together by pins, so members are free to rotate, which means that they can only apply forces in the direction that the member is oriented. We also assume that the weight of the members is negligible compared to the load placed on the truss, so we can neglect the weight of the members in our computations. Let's look then at pin A. Pin A, we had this force FAY. We have a force to the right, which is TAC, and a force up and to the right, which is TAB. And because I have equilateral triangles, all of my angles here are 60 degrees. At these pins, we can only apply the sum of the forces in the x direction is 0 and the sum of the forces in the y direction is 0 because these are points, and so we can't look at moments about points. I will have components of TAB. I'll have a horizontal component here. This is TAB cosine of 60 degrees. And I'll have a vertical component. This guy is TAB sine of 60 degrees. And I won't go through this in this sort of detail in the rest of these joints, but just to make sure it's clear, I've got an angle of 60 degrees here. I've got TAB on the hypotenuse, so this part here is given by TAB times the cosine of 60, and this component here is given by TAB times the sine of 60. So let's sum in the x direction. And in the x direction we have TAB cosine 60 degrees plus TAC is equal to 0. And if we sum then in the y direction, we have TAB sine of 60 degrees plus FAY is equal to 0. And remember, we've already computed FAY, so we know this guy here is 500 newtons. So we can solve for TAB. So TAB will be equal to minus 500 newtons divided by the sine of 60 degrees minus 577.4 newtons. Okay, so if you get a negative sign as a tension, don't worry. What it actually means is that the member you're looking at is in compression, not tension. So taking this number, plugging it in here, and solving for TAC, we find that TAC is going to be 577.4 newtons times cosine of 60 degrees, 288.7 newtons. The next joint we'll look at is joint B, and we know that here we'll have a tension TAB, which we've already found. So we'll use joint B to find TBC and TBD. At joint B, we have tension TAB, tension TBC, and tension TBD. These are forces. Their magnitudes are unknown. We know their directions because we know the directions of the members. And again, we know that the angles here are 60, 60, even though I haven't drawn it very well, and 60. Let's look at the sum of the forces in the x direction. Minus TAB, because it's pointing to the left, cosine of 60 degrees, plus TBC, cosine of 60 degrees, plus TBD, and this is equal to 0. So we know the value of TAB, but we don't know BC or BD, so we will have to look at the sum of forces in the y direction. And here we have minus TAB sine 60 minus TBC sine 60 degrees is equal to 0. Okay, this is the component of TAB and TBC in the vertical direction. TBC is equal to minus TAB, And we know that minus TAB is going to be 577.4 newtons. This is from a value that we've already computed. If we now take TBC and plug it in here, we'll have then minus TAB, which is minus 577.4 newtons, times cosine 60, which is 1/2, plus 577.4 newtons, this is TBC, cosine of 60, which is 1/2, plus TBD equals 0. And when we solve this, we then get TBD is equal to minus 577.4 newtons. Minus 577.4 newtons. TBC, 577.4 newtons. Again, we're making great progress here. The next thing we'll do is we'll look at joint C and do a free body diagram there. We know TBC, we know TAC, so we know that I'm also drawing the arrows backwards because I've got a cat that's in front of my screen. One should never allow cats to get near one's computer. Now we'll find TCD and TCE from a free body diagram of pin C. We have TAC, TCE, TBC, and TCD. We also have a load, and the load is 1 kilonewton. And all of these angles here are 60 degrees. As we apply sum of forces in the F direction is 0, and this will give us minus TAC minus TBC cosine of 60 degrees plus TCD cosine of 60 degrees plus TCE is equal to 0. And if we look in the y direction, TBC sine of 60 plus TCD sine of 60 minus 1 kilonewton is equal to 0. And we know what TBC is. We've already computed this. And so we can then solve this equation for TCD. I'm not going to go through any of the details here. We can solve it for TCD being 577.4 newtons. We can then take this expression for TCD, plug it in here. We already know TAC, TBC, and so we can get then that TCE is equal to 288.7 newtons. We had TCE is 288.7 newtons, and TCD was 577.4 newtons. We're almost done, and hopefully you're beginning to see that there's some symmetry in these relationships, so we ought to be able to predict what the tension in member DE is just by looking over here, but we won't. We'll go through the whole thing in brutal detail. The thing to note, though, is that I have only one unknown left. We have found all of these guys that I've drawn arrows for so far. So now the only thing left to find is TDE. So I can look for TDE either at joint E or joint D. It doesn't really matter which one I choose. Actually, let's look at joint D. The free body diagram of pin D, I have TBD going off, I know that. I have TCD, I know that. I have TDE, which I don't know. I'm going to go straight to the summation of forces in the y direction is equal to 0. The reason I'm going to do that is if I do this, then TBD isn't going to show up in the sum of forces in the y direction, and it'll make life a little bit easier. So I have minus TCD times sine of 60 degrees minus TDE sine of 60 degrees equals 0. And I can solve this then for TDE, because I already know TCD. So I solve this for TDE is equal to minus 577.4 newtons. Okay, so I'll go back to my free-to-body diagram and write this in. This is minus 577.4 newtons. The members where the tension is negative are actually in compression. So, for example, this member here, joints D and E are pushing towards each other. Joints B and D are pushing towards each other, and joints A and B are pushing towards each other. The other members are in tension, that is, they're being pulled apart. The internal members are being pulled, and the members on the edges here are being compressed. That pretty much wraps up this video. I hope you found this example helpful.